Hi guys, welcome back. In this problem, we are being discussing a problem from Pathfinder BYU21 from Magnetism chapter. So the problem says we have a ring of radius r made of an insulating material, has mass m and carries uniform charge. Initially, it rests on a frictionless horizontal tabletop with its plane vertical, a uniform horizontal magnetic field of induction B pointing everywhere parallel to the axis of the ring is established in the region to the right of a vertical plane A as shown. The ring is pushed forward to acquire velocity v0 without any rotation. What should the charge on the ring so that it starts rolling on the tabletop after completely entering the region of the magnetic field? So guys, in this question, first we analyze the initial situation of the ring before entering the magnetic field. So before entering the magnetic field, it has a translation velocity v0. So it only translates, doesn't do any rotation here. So the we showed here weight mg downwards and normal upwards. Okay, so after completely entering in the magnetic field, it starts pure rolling. So before it doesn't start any pure rolling. Even after entering half of the ring, it doesn't start any pure rolling. So after entering completely, it starts pure rolling. Okay, so in this case, the change in kinetic energy is zero. So why means, so the work done by the gravity is zero. So why? Because the velocity and gravity are always perpendicular. So the work done by normal is also zero. As we know, magnetic force doesn't do any work. So the from work energy theorem, change in work done equal to change in kinetic energy. So the work done is zero in this case. So the change in kinetic energy is also zero. So from this we write Ke initial equal to Ke final. So the initial kinetic energy is half mv naught square. So final kinetic energy is half I omega square plus half mv square. From this we can find v naught by root 2. So omega is angular velocity after pure rolling. So yeah, from this we can find omega equals to v naught by root 2 r. So I written here one statement: the complete translation kinetic energy is converted into rotational kinetic energy. Why? Because so at general time t, I drawn here a diagram. So at general time t, we have considered an elemental charge dq here. If we look from center of mass frame, it has a velocity v in the horizontal direction and the tangential velocity r omega. Okay, so if its length is d theta d phi, so if we drawn two lines here, each of making angle theta with the horizontal. So if we observe only this part here, so it has a velocity v and r omega tangential. So if we do v cross b here, so from for velocity v, we get df force perpendicular to it. So for r omega, we get df dash perpendicular to it. So alright. So the work done is zero for df and v. So why? Because both are perpendicular, but these two do work. It is the positive work they both do. So and these two will do work. These two will doesn't do any work because they are perpendicular. Df dash and v participate in work done, so they do negative work. All right. So the negative work is done by translation velocity. So by this we can understand that translation kinetic energy is decreasing. So it is doing positive work. So the rotation kinetic energy is increasing. So by this we can say it after it entering into magnetic field, it starts pure rolling. All right. So if we write the equation for torque here about center of mass, d tau equals df into r cos phi. So r cos phi here is perpendicular distance. So basically this length is r cos phi here. Okay. Okay, I'll show here. So this length is r cos phi. Yeah. So df dash doesn't participate in torque equation because it passes through center of mass. Okay. So for df, we know formula dqvb. into r cos phi. I wrote here dq as linear charge density into r d phi, as we know. Okay, so x is the displacement of center of mass. From this we get the velocity v here. So x equal to r cos theta. So if we differentiate with respect to time, we get v equals minus r sin theta times d theta by dt, equation 2. Okay, so I multiplied with torque with 2. Why? Because so we are writing only torque for this only, so we have only two elements here, so I multiplied it by 2. So after integrating cos phi d phi from 0 to theta, we get total torque equals 2 lambda bv r square sin theta. So we assume this as equation 3. Now we write equation for angular impulse here. So by writing equation for angular impulse, the question is not getting any complex calculations. So we avoid complex calculations here by using equation for angular impulse. So the angular impulse is written as tau dot dt equals change in angular momentum. So if we substitute torque here, 2 lambda bv r square sin theta dt equals I dot d omega. So why I write d omega means the angular velocity is changing with respect to position and time. Okay. In the place of velocity, we substitute equation 2 here, minus r sin theta d theta by dt. So dt cancel here. So from this we get minus 2 lambda b r cube sin square theta d theta equals mr square into d omega. So we can easily integrate it. Basically it is in the integrate form only. So we integrate sin square theta from 0 to pi here. Why 0 to pi means, so it is 0 degrees after it completely enters. So we have taken half of the circle for one element here. So 0 to pi. Alright, next. So for we are integrating omega. Initially omega is 0, as you know, it is pure rolling. So finally it enters into magnetic field. It has angular velocity omega. So from this actual integral of sine square theta, we write this as 1 minus cos 2 theta by 2. So we can integrate this easily. So yeah, okay. So substituting linear charge density as q upon 2 pi r, as we know here. So after doing some simplifies, q equals root 2 mv naught by br. So the charge of after pure rolling is q equals root 2 mv naught by br. So this is interesting question from Pathfinder. If you like the video, do like and do subscribe, guys. So see you in the next video.